Let's first look at the lattice method, or we'll call the tree method. So, you can build a binomial tree which have 2 branches, or a trinomial tree which will have 3 branches each step from each node earlier. Now, what's the advantage, disadvantage? Well, for tree method, it's actually very good for American style options where you have a early exercise opportunity, or some of the Bermudian style derivatives as well. And if you have, even for European ones, that if it doesn't have a closed form solution, you can always then use a tree method to calculate that. Now, obviously, we're gonna go over how we're gonna construct trees and gonna price trees, price options through the lattice method. I'm sure some of you have seen it, so I'm not gonna go into a lot of details, but I'm just gonna give an overview of how the tree method is actually generated and constructed and used to price options. Now, it's known that the lattice method is actually difficult to work with path-dependent options, because then path-dependent options you have to build non-recombining trees, because each path will be different. And then in that case, you will have a problem where the branches will become too big. Then the number of branches becomes really substantial when you go a few, decent number of steps. Then makes it numerically infeasible to use as a procedure. Between binomial trees and trinomial trees are obviously easier to construct than trinomial trees. But trinomial trees, because of the you have one more branch, so from each node, trinomial tree has 3 branches. Therefore, trinomial trees can actually incorporate additional features much easier. Like, for example, the mean reversion structure. So therefore, you tend to see trinomial trees utilized in places where you need to price interest rate options, where the 3 branches out of one node allows the interest rate process to have mean reversion. Between the lattice method and the numerical PDEs, we can actually see that if we implement an explicit method for explicit finite difference method for to solve PDEs numerically, then that method itself effectively produces a trinomial tree. So there's a connection between the numerical methods in solving PDEs with the lattice method. Let's see how we can construct a binomial tree. So essentially, to construct a particular time step of a binomial tree, we have 3 variables that we can specify. So essentially, P, which is probability going up, then obviously 1 over P is the probability going down. Then U and D is the magnitude of going up, and D then determines the magnitude of going down. Now, you have 3 variables that we can choose. So in order for us to be able to work with a binomial tree, we have to have an additional condition to force the solution. So we have typically we have 2 choices. You can have more than that, but one of the 2 well, the two most popular choices are, one is we force u to be equal to 1 over d, okay? So therefore d is 1 over u. And the other choice is that, say you can fix p to be 0.5, then 1 minus p will also be 0.5. So in the second method, the probability going up and the probability going down is the same. And so they will have a tree from the expansion of the tree. You actually see them being quite symmetric in that nature. Sometimes that symmetry is actually useful. So that's why people sometimes make this choice. So what do we do to construct trees? Well, we obviously want to match two moments, right? So we have 3 parameters to match 2 moments, and we need additional condition to make that happen. Now, why do we only need to match the first 2 moments in constructing a binomial tree? Well, the answer to that question is that when we deal with the discretization and under most of the frameworks that we have, we were actually looking at a resulting distribution that is either normal distribution or log normal distribution. So in those cases that you only need to the first 2 moments to determine the entire distribution. So if you recall from statistics, you have a normal distribution or not normal distribution, the entire distribution is only specified with the first 2 moments, okay? That's why as soon as you know the first 2 moments, you really know all the entire distribution itself. So while handling the path dependence features, dependency is problematic. While it's really, as we mentioned earlier, I think I mentioned that quite some time ago, even in some of the previous lectures, that well, for a binomial tree, your tree will grow 2 to the power n branches. So that becomes exponential. It will grow exponentially. So when n is some relatively big number, then 2 to the power n is a very big number. So if we produce a binomial tree, typically a binomial tree will look like this. And so u, say, is 1.2 and d is 0.8. So as, say, some value 100, so it'll be 1.220, so there'll be 80, right, and so on and so forth. So that allows us to build the stock prices at each of those nodes. Okay, let's take a look at how we build a binomial tree with this additional condition where u equals 1 over 1 divided by d. Now, to match the first 2 moments, we have this condition. So this condition is PU, probability of times the up movement, and plus 1 over P times the down moment. And this is the expected drift. This is basically the drift, which is the expected value. So this gives the first moment. And this basically then gives us the condition for matching the second moment. Okay. Now, once you have that, we can solve that. P is really A minus D divided by U minus D. Where A is just this value here, which is this. thing here. And you have P, you have U, you have D. So we'll have 3 choices. And because of this condition here, we can determine all 3. Okay. Having this U term like this give us a fairly good numerical efficiency. But there may be reasons that people wanted to not using a U equal to this particular thing, so they may specify a different U. Then they can also do that if they have a different U than this, then they will have a different D, but still keeping U is equal to 1 over D. And given that, then they can, have a different P here, but the condition is still P equal to A minus D, U minus D, and we can then still construct a usable tree as well. Let's take a look at an example how we price an American put on a non-dividend paying stock, under the lattice method. So suppose we have the initial price of the stock is $50. The strike is also $50. So we have an at the money option here. Interest rate very high, say 10%. We're looking at 5 months as maturity. And we decided to use a time step of 0.0833. This is basically 1 month time steps here. Typically, it's this in practice, you probably have a lot smaller delta t here. But from that, you as an illustration, we can choose a delta t that is relatively big. Now from that, we calculate an A equal to 1.0084, and U, based on this, we would have the in this case, we have chosen a particular value of U. So, and then D is 1 over U. So this particular choice of U determines what choice of the sigma we actually have. But in any case, that given the choice of U, and then with D, we can calculate a P, which is equal to 0.5073. Now, if we do that, we basically says that if we start at $50 for the first 2 nodes, one is 12% higher or 11% lower, then the first one is 50 multiplied by 1.1224 will give us 56.12. And if we have 50 multiplied by 0.8909 will give us 44.55. And then we can do that. So continue to, this was multiplied by U, multiplied by U, and multiplied by U, and so on and so forth. So we can construct what the stock price is. So the first one, the upper numbers here are the stock prices that we generated under the binomial tree here. Then we look at the payoff at the last time step. So because our strike price is $50, so anything that is above this, so above 50, there'll be the payoff for the put, they're all 0. But here the payoff the put is 545. And for this one is 1464, and for this one is 21. 93. So for those three nodes, we were exercised, and we'll have a payoff here. Now, there, if you see that the red one is where exercise is optimal. So in this case here, we can calculate a expected value based on the P we have between this number and this number here. You will find that the expected value is actually lower than this exercise value. So we will not wait and we'll exercise here. So this is this will be the option value if we exercise. And same thing here, the exercise value is better than the average value that we have for the payoff in the last node. So we'll exercise here. This one too, the immediate exercise value is better than the expected value of the payoff in the earlier one, so we exercise. However, for situations like this, the expected value from here and here is actually better than the immediate exercise value. Because you see that the immediate exercise value will be 0, but your option has a positive number if you wait. Okay, same thing here. Well, you will not exercise because the exercise value, if you exercise, I mean, you wouldn't exercise if the stock price is higher than this strike. And you can see for this one here, your exercise value is $5.45. But if you wait, which will take the expected value of this number and this number, you get $6.38. So you can work out of each node from the last one forward. So this 2 will determine this 2 will determine that, and this 2 will determine this 2 will determine that, and so on and so forth. So you can work all the way back to get the numbers at the bottom, and until you get to this point, then you compare the intermediate exercise versus the expected value, and the expected value is $44.49. Now, this means this will give us the price of the American put being $4.49. Okay. Now let's take a look at how, that we don't use the condition of U equal to 1 over D. We use the condition where P equals to 0.5. So then obviously you don't have to determine P, you have the P there. So 1 minus P is also 0.5. You need to determine U and D based on the two equations that you match the first two moments. So basically you need to use these two equations once you know P is 0.5 and to calculate what U and D are. Now in this case, because P is 0.5, you have a symmetry in terms of probability, but you do not have symmetry in terms of the value of the stock price, because the value one time period earlier is not really in the middle, because you don't have U equal to 1 over D. So this can actually may not be that convenient if we want to calculate some of the sensitivity parameters, because your U may be really big compared to the D here. So one of the jump may be really large, that is too large for you to be comfortable getting a good sensitivity number. So in those cases, you may have to shrink the time steps in order to get good sensitivity parameters like delta, gamma, and so on. But in this case, the advantage is that the probability, they're all symmetric in probabilities. So the probability of going to the uppermost node is the same probability of going to the lowermost node. Now we have talked about binomial tree for non-dividend paying stocks, and through building that, we then obviously can price options for where the underlying stock is not dividend paying. But how do we handle the underlying stock where the stock pays dividend? This can actually have certain implication. The payment of dividends can have certain implication to our tree building. Essentially, if we don't handle it well, we could end up with a non-recombining tree, and that will be undesirable. So the goal is to properly handle dividend payment such that we do not end up with a non-recombining tree. If dividend is paid in such a way that it's paid with a known dividend yield, then what we can do is we can reduce the price of the stock by the total dividend yield between the time steps. And we can do it as a ratio. Then we would, by doing it in such a way, we will still preserve we will still preserve the recombining tree. So to illustrate that, so basically, suppose this is the first time step, and between the first time step and the second time step here, there's a X dividend date, okay? Then here, you need to reflect the dividend payment. So essentially, dividend payment is a ratio, is a percentage of the value of the stock. And the value of the stock without dividend payment is S naught times U square for this one. And this will be up and down, so this will be S naught, and this one will be S naught times D times D. And then this is the pre-dividend stock price. And then the dividend payment is a percentage, a constant percentage of that stock price. So then your tree here, you then start at a different point after the dividend, not at this point here is get dropped off by this 1 minus delta. But after that, until the next dividend payment, you still okay, because here there are 3 points, you have 3 situation after the dividend, and after that you still have a recombining tree here, because this one going down is really this thing going up, because you have S naught U square times this, then times D. So and D is equal to 1 over U. So this becomes S naught times U times 1 minus delta. And here, you've gone down to this thing here, and then it's just S naught times 1 minus delta, but then you go up 1 step, so it becomes S naught times U times 1 minus delta, which is the same point. So if you handle it proportionally here, you still have a recombining tree here. So after 2 going up, 1 going down, is equal to having 1 down and 2 ups like this. You still end up to the same point. Now note that this value, they're all different, although it has the same portion here, because this is the same portion times a bigger number. This is the same portion times much smaller number. So this distance actually should be smaller than this distance here. Okay, but it's proportional though. Therefore, by implementing this way, you have the a preserved recombining tree. Also, one point to actually realize is that this delta here, although I have the same delta, we just use one delta here. But let's say if you have another ex-dividend date here, then between there's a drop. If there's a drop here, then that delta doesn't have to be the same as this delta. So this thing here, you can call this delta 1 minus delta 1. So if the ex-dividend date is here, then the value realized here will be S naught times U to the power 3 times y minus delta 1, then times 1 minus delta 2. Okay, and that delta 2 and delta 1, they don't have to be the same. Okay, so in that case, you can handle the situation where as long as you paid a dividend rate Q, but your dividend rate for each dividend payment date can actually be different. Now, if the dividend is actually paid in an amount rather than so in a known amount rather than a known proportion, we have to be extra careful to avoid not having the tree being non-recombining. Because if we just simply reduce the dividend, the stock value after the ex-dividend date by this same known amount of dividend, then we will end up having a non-recombining tree, which is very undesirable. So to see that, so if we have S naught, so the first step we have S naught times U, this one is S naught times D. After that, the ex-dividend date is somewhere here. Then if you have S naught times U square minus D, and here you have, S naught times U times D, which is 1, then times S naught, we just get S naught, so S naught minus D. And this one is S naught D squared minus D. Now, once you get to this point, here the tree will not be recombining because here is S naught times U squared minus D bracket times D, the little d. And this point is S naught minus D bracket times U. So if we multiply through, you have S naught U minus D times U, which is different than this S naught time. If we multiply D here, you get S naught times U, but then you have minus D times big D times little d. But here you have S naught times U, but you have U times D rather than D times D. So these 2 points are different. And then because these 2 points are different, then you're gonna have non-recombining trees. Every time you get an ex-dividend, you got a dividend payment, you're gonna have extra branches together, branching out of this tree. So your tree can become complicated. To solve the problem, we have to take the tree apart and handle that tree with two components. One component is related to the certain value of dividend payment, and the other component are the stochastic movement of the stocks, which is not related to the certain payments of dividends. So in this case, then we essentially we're looking at a process for S star, which is whatever the actual S minus the present value of the known dividends. And essentially, we're building a tree for S naught, okay? And the stochastic movements or everything is related to this S naught rather than with original S. Let's see how that is handled. You see now in this particular tree here, although the stock value is actually S, we're actually building a tree for SA, which is SA is equal to S minus the present value of the dividend payment. And we know the dividend this is the ex-dividend date, and is in this case 1, 2. So this is actually paid at 2.5 years later, just for illustration purpose. Then that's the present value of the known dividend 2.5 years from today, and taking the present value of that, and our current S price is already subtracted by this dividend payment. Then whatever is left, which is this SA, is the stochastic component of it. Now we're building a tree for that. Okay, so we're building SA, so this becomes SA times U rather than S times U. And this becomes SA, and this is SA times D. And SA times D then times U becomes SA again. So we have recombining trees here, but they're all multiples of SA. Now after the dividend payment here, the dividend payment right here, right? The actual value here is actually SA times U to the power of 3, because after that, the dividend of D has been paid. Now, obviously, that when we calculate the option payoffs, we're not really using SA because we have to use the actual stock price. So there are places where SA times this thing here is actually the stock price at this node, but they may not always be the same. So here I have traced out what the actual S prices at the different points. So the actual S price at this point is really S one step upward, which is SA times U, which is this value here, but you have to add the present value of the dividend, but the discounting is actually one year less because you're already 1 year past that. Okay, so here you discounted 2.5 years, here only discount 1.5 years. So the actual stock value is this at this point. And the actual stock value at this point is this SD here, which is this value of SA times D. You add back the present value of the dividend. And for those 1, 2, 3, the actual stock price value are given by this. So here you only discount that by 6 months. And here, because you pay the dividend already, so your stock price here, when you calculate it, is just SA times U to the power 3. Because, you will add this 2.5 minus 2.5. So this will become, so you will have this thing equal to that one plus D, but then you pay the D at this point here already. So then after you minus that D, you will have this value, okay? So after you pay the dividend, you then becomes this number here, which is this. So this number and the actual stock price becomes the same. Now you can continue. And then when you continue, you have to, if there's no more dividend payment, you just continue from here, multiplied by U, multiplied by D. And so if you have an American option where you can exercise at different times, then it's okay to, let's say there's no more dividend payment here, it's okay to use those values for the stock price to calculate your payoffs and discount and calculate average to the points before. And however, when you get to this point, for example, if you calculate the value between early exercise and the average, then the value to use to calculate early exercise, let's say is American put, will be the stock price here minus K, will be K minus the stock price, let's say American put. Then that K minus the stock price here, the stock price that's minus from K is not SAU square. Instead, is this SUU, which is SAU square plus this value here. So because you haven't paid the dividend here. Okay, so that value of immediate exercise will be different. So the value you calculate, the waiting time will be whatever payoff you hear from here, discounted to a point earlier, and the payoff here is calculated essentially is related to SA here, right? SA U to the power 3, SA U to the power 2 times D, and it's K minus this, K minus this, and then you discount it back. But for here, it's K not minus this thing here, but K minus this thing plus this D here. Okay. Now, trinomial trees will be different, and let's take a look at trinomial tree in the next video.